Alright, so we had actually started with module 2, which primarily deals with the mathematical fundamentals leading towards the algorithms for cryptography. So in that we had discussed a few points on last day's class, especially the Euclidean algorithms, and we have tested with some of the examples, and in that light we had come to a conclusion that we require something called as the information on additive inverse and multiplicative inverse. Multiplicative inverse we have already used in certain algorithms. Additive inverse we have not used that much, but maybe sometime later we might use it. And by terms of additive inverse, we mean it that if two elements A and B, we have a addition plus, and we divide that by the modulo n, like the remainder will be 0. If the remainder is 0, we call it the additive inverse, and in that one of the examples we consider as Z10. As I said, Z10 here indicates that it is a modulo 10 and n that is equal to 10, and in that we can see that this many number of sets are present, which eventually will mean that, for example, the third one, if you consider 2 and 8, so 8 plus 2 is 10, 10 divided by 10, because our modulo n is 10 in this case, so the remainder is 0. So like that we are also trying, I think we took an example of Z15 also, so similarly the sets can be generated. On the other hand, the multiplicative inverse, which we are pretty much aware of, that gives us an information that A multiplied by B will give us a product which when divided by modulo n will have a remainder which is equal to 1. And in that context we have found out there are two ways of finding it. One is the hit and try method, where we have to substitute one after the other the elements for which the resultant is 1, or else we can use the GCD technique and we can find it out. So this is just because it is there with us, maybe I'll just brush up once again that what is the multiplicative inverse algorithm which we already had discussed. So if you remember, this was the algorithm and this was the exact example that we have discussed. In that also you can see R1 and R2 will be initiated based on, please see the change. Now since we have done the Euclidean algorithm for GCD, see the small little change that we are looking at. If you observe the R1 and R2 over here, in Euclidean algorithm we were taking it as A and B to be R1 and R2. Whereas in over here, the modulo operator 26 has come as R1, whereas R2 is the element on which you have to find the multiplicative inverse. So this is a small little difference that you are considering over here. Please make a note of it. The rest of the things are almost very similar. Like for example, the R over here, which is the remainder, okay, that is same as that of the previous example itself, R1 minus Q into R2, so that's the same thing. And we also have this T1 and T2 as two elements, so very similar to the extended Euclidean algorithm that we have discussed so far. At the initial stage when we discussed about multiplicative inverse, at that time we didn't knew about Euclidean algorithm, so it was a little like applicative, that's why we introduced there. But now since we know the Euclidean algorithm, so T1 and T2 will be initiated as 0 and 1, okay, and then we have to find out T, which is equal to T1 minus Q into T2, which was already there, we discussed in previous day's class as well. So keeping that in mind, okay, can you please find me the answer for this, where you have find the multiplicative inverse of 23 in Z100 using the Euclidean algorithm or the process of the multiplicative inverse algorithm. Please take a moment to finish this now. Since it is already being done, I am not wasting much time on this because we have a different set of discussion, very important, which we have to discuss today. Kindly take your time out, make the table. You have R1, R2. I will just give you this table for you for your reference. Please make the column ready. Q, R1, R2, R, T1 and T2. Few assumption, again I am repeating it. R1 and R2, you have to mention it with respect to the R1 should be the modulo n operator. In our example, the one that I am giving you, n is equal to 100. So your R1 will be 100 and your R2 will be that 23. Alright? And you have to initiate this also. You please make a note. T1 and T2, it should always be 0 and 1. So please make a note of that. Accordingly, from the table, give me the final answer for the multiplicative inverse for 23. I am keeping this table just for your reference so that you can see the column for your liking. The data are different over here also. Because at initial stage when we discuss about multiplicative inverse, remember at that time we only had Z26 because the alphabets were of 26 letters. But now since we are discussing the multiplicative inverse in context to discrete mathematics, the base will change. So now as in our case, the base is 100. It can be anything for that matter. So that's why we are practicing the element 23 in Z100, which is similar to the one that we discussed in the last class. And find me the element B. That's the So if you remember, this was the answer actually. I don't know whether you were able to deal with the last line that you are looking at. So whatever you are looking at T1, whatever you are holding as a value of T1, that will be considered as the inverse. So you can see over here also the example, -7 was there, and that's why -7 has been considered over here. But as this is negative, we cannot consider it. So that's why 26 has been added to it, and that's why the 19 will become the answer. But for your case, I don't know 23 how much will come. So this is the table for you. Okay, this will be the table. As rightly pointed out, it was -13, so we got that. And naturally, negative we cannot consider. So 87 will be the final answer, which I got from one of you. Any doubt with anyone with this calculation? I'm not investing much over here because we have done this before itself. So it is just a recap of what we have done already. So no point of discussing further. Hopefully, all of you are aware of it. But in most of the cases, you will find that when we do the Chinese remainder theorem, or even now, you will find in some cases you will require to find out this multiplicative inverse. In many of the cases, what I have observed, that the trial and error method will be sufficient to analyze, because only if it is specific to multiplicative inverse calculation, you will require this process to go through. Other than that, the questions which I came across, there the trial and error method will be relatively easier to find out that what the values are for the inverse I am talking about. So that is also an alternative way of doing it. So, but this is actually the algorithm how it should be, right? So this is about the multiplicative inverse. The rest of the this is again very similar. So I'm not repeating it. You can take any n number of examples. The reasons will be the same. This is basically, we call it the addition and multiplication table. If you observe very carefully, this is the additive inverse. You can see the addition. This is for Z10. So when you have 10 elements, how we are going to arrange it. And if you observe that properly, when we are looking at additive table, it should be a plus b, which is relatively equal to 0. Like the remainder will be equal to 0. So wherever the zeros come in, you can see over here, 9 plus 1. For example, this one, last one, 9 and 1. Wherever it intersects, it will be 0. Alright, so that's why how it is being mentioned. So this 0 indicates the element, the condition for the additive inverse, whereas the 1 that you are looking at over here, they are all indicating the multiplicative inverse. This is for Z10. Similarly for Z15, Z20 or any other modulo, the table will go on changing itself. So that's just a snippet of any one. Right. So now we come to different sets of addition and multiplication. Alright, this is again just a nomenclature that you need to understand. You can observe that one in the left hand side that you are looking at Z6, for example, over here. Z6 will have 1, 0, 1, 2, 3, 4, 5. Okay, so that Z6, if the representation is of this nature, okay, we will usually call, you can see we need to use Zn when additive inverse are needed. That's a nomenclature I'm talking about. The nomenclature is of that. Whereas the right hand side, if you see Z6 inverse or star, if you call it, that usually serves for the multiplicative inverse representation. So if you observe that for the first one, that if you consider Z6, you have the element 1 and 5. Okay, so 1 and 5 are the two elements for which the multiplicative inverse exists. So that's the point. Okay, so we have to, in the same manner, you can try and find out that what are the multiplicative inverse. Can you tell me for Z6, if you consider 5 as the element, what should be the multiplicative inverse of it? Very quickly you can say, without involving with the algorithm. 5 is the element. See, suppose here 5 is the element. What should be the multiplicative inverse of 5 for the set of Z6, where the modulo operator is 6? Can you quickly tell me? Just use the process of hidden trial method. What is the element? 5 multiplied by 5, if you say. So 25 divided by 6, so it's 24, so the remainder will be 1. So basically the remainder is 1 for 5, so 5 has a multiplicative inverse which is 5. Like that. So similarly you can take for any other set, and based on that you will find that the elements at times it might be same number. For example, Z7, if you observe, the additive inverse are 0, 1, 2, 3, 4, 5, 6. And in the other hand, the Z7 star will have also, except for the 0, 1, 2, 3, 4, 5, 6 as the multiplicative inverse. Again, for example, Z10 will have less number of elements for multiplicative inverse. The point is that the condition should be met by the individual element. And if you remember another condition, I don't know how many of you figured that out. In almost all the cases, we had tried to prove the first point over here, that the GCD will be 1. In over here, this is the example that we have considered. So 100, 23, that is equal to 1. So that's also a testing criteria that you have to consider. That whether given the element for which we are trying to calculate the multiplicative inverse forms GCD equal to 1 with the modulo operator or the modulo n. So that's also testing condition. We have already discussed that previously. Okay, so I thought of skipping that. So just to remind you once again. Alright. Now if you observe this one again, just to get back once again. So 12, suppose the question is to find 12 and its multiplicative inverse. The problem is 12 and 26, if you consider, they are not equal to 1. So naturally 12 will not have a multiplicative inverse for that matter. So it doesn't exist, but for that matter you can see that even if you calculate the table, the final answer will not be equal to 1. So this is not equal to 1, that's a proof. So basically you have to, whenever you try to find the multiplicative inverse, the condition is the GCD of A comma B should be equal to 1, where A and B are the n and the element that you consider. Okay. Right. So that's all for this part. Now this is where our discussion starts, where the algebraic structure and the discussion of group, rings and fields will come into picture. Now this is a part where it's purely based on the discrete mathematics and its application area. For the time being, whatever we are going to discuss, this is relatively not related directly to the application of cryptography as of now, but we will use this concept at some time later. Okay, so for the time being, let us try to find out what are algebraic structure and how the groups feel. Hopefully I'll finish off with the group today itself. So how these can be described and all, because they have certain properties, and based on which you have to test and verify that whether a certain operation or certain condition can be classified into groups. Alright. So for that purpose, let us see once. First of all, let us see the first line itself. Cryptography requires set of integers and specific operations. Alright, that are defined for those sets. Okay. Now again, so what we have observed, that we are now familiar with manipulating with the data, how we can manipulate, how we can operate on set of data. We have found out that there are certain conditions that we can impose on the data set for which we can conclude something. Now we are arranging the data into some certain sets. For that to become a particular set with certain properties, we are defining the algebraic structure. What exactly are those things? I'll discuss that after this. The common algebraic structures which we have is group, rings and fields. Alright, so let's see about group first. Please make a note of these properties. I'll go one by one very slowly and we will try to prove as much as possible for this segment. So a group G is a set, because in general it becomes very vague if you don't take examples to prove it. So I'll take some examples to make sure that you understand this carefully. A group G is a set of elements with binary operation star or dot. Now first of all, the point you might have is that, sir, is this multiplication? The answer is no, this is not a multiplication sign. Okay, dot here indicates an operation. It can be an addition, it can be a subtraction, it can be a multiplication, even it can be a division based on certain criteria. So this is basically an operator sign. Okay, please make a note of it. So a G is a set of elements with a binary operation that satisfies 4 properties. Please make a note of these 4 properties, because I will go back to the writing pad mode so that this will not be there. First and foremost is the property of closure. Okay, the closure property says that if A and B are in G, then A operator B is always in G. The first property that you observe. Now before going further with the other thing, I think better I'll go and explaining one by one the properties, and let's come back to this slide again and again so that we are in a good position. So for the time being, please make a note of the closure property only. Just write down the closure. Rest of the things will come one after the other. So let me just open this journal file. Alright. So we define this as binary operation. Okay. So by definition, let's first define the binary operation, the dot sign that you are defining. So please make a note, if there is a non-zero set G, if there is a non-zero set G, because G is what we are defining in the PPT as well, then the binary operation means, okay, in general, that there exists a function, maybe we define it as f, such that the operation would generate a new element that belongs to G. So that's the definition of a binary operation. Okay, and as we are doing a binary operation, because we are getting one output at the end, that's why we are calling it as a binary operation. We are getting two input and we are getting one output out of it. So that's a binary operation that we are talking about. As I said, the operation, this is the basic definition of a binary operation. Alright. Now as I said, plus, minus, subtraction, anything can be a binary operation. So suppose I have a scenario where G is given by minus infinity to minus 1, 0, then plus 1, 2. So any integer. Suppose G is an any integer set, non-zero set. Now suppose you apply any of this rule. For example, you take G, the representation is something like this, G plus, and this is the nomenclature of it. Okay, G is the set of elements which we look into, and plus is a operator, a binary operator on that particular set. Now this set can be anything. For example, it can be rational numbers, it can be in real numbers, anything for that matter. Okay, we'll see that if time permits the example we gave. So suppose G plus, what does that mean? It means that given the set G, which starts from minus infinity to infinity as the integer set we all consider, we will take any element from that set and we will operate on plus, and we will get a new element which will be the part of that set itself. For example, you take around like, for example, 5 plus 10, so 15 the answer. So this operator plus on top of the two elements 5 and 10 which belongs to G generates a new element 15 which is also part of the set. Understood? But suppose I write check G as the same set, will minus be considered as a binary operator? Will that be considered? Yes. Why? Because if you consider an element 5 minus 2, that is 3, part of the set, and if you consider 2 minus 5, that also is part of the set. But suppose I change the set to all positive integers. Now you can see n I have written. So the set changes. Important, right? The set has changed. Now capital N, which means all natural numbers, so it starts from 0 to end at infinity. All positive numbers we have. Now if I consider that, will plus be an operator on top of it? Will plus be a binary operator? The answer is yes. But will minus be an operator? If you check here, if I take 5 minus 2, it becomes 3, which is a part of the set, the minus operator. But if you take 2 minus 5, which is minus 3 doesn't belong to the set. So that's why the set which we are considering for our example for our reference becomes very important. So one operator might be called as binary operator on a particular set. It might not be an operator for the given particular set. So same example of this. Okay. Same way you can see that multiplication operator. If I consider multiplication operator, that also will be very similar. But if you take division, 5 by 2, 2.5. It's a fractional number. It doesn't belong to the set. So naturally, division will not be a binary operator on top. Right? So that's the basic example of a binary operator. Clear everyone? Why this is binary operator? Why we are considering? So basically in the PPT, the dot sign indicates either a plus. So in general, we can write in the PPT it is mentioned something like this. G dot. Don't confuse yourself dot with a multiplication. Here, for our discussion, multiplication in all times will be mentioned something like this. Star. Okay, the conventional dot is usually used for multiplication, but here in our discussion, dot is not the multiplication. It's just a binary operator we are talking about, which has a property of this nature. Right? Now, the property by which a binary operator makes the resultant element to be a part of the set is called the closure property. That's what we have written right now. If you go back to the property, the first property, if A, B are in G, then A dot B is in G. Now dot we have defined as a binary operator. So a binary operator applied on two of the elements of a particular set, if it makes the new element to be part of the set once again, then we call it the closure property. Any doubt with the closure property? Anyone? Because that's the fundamental starting point of all this discussion. Yes, natural numbers here. Correct. It's okay. Yeah. It should be satisfied for all the elements. That's why minus won't be considered as a binary operator for n. If you consider a set as it won't be considered. It should satisfy for all the elements in the set. Naturally. Right? So this is the first property that we are looking at. So closure property has been defined. Now, if a non-empty set, please make a note of it. If a non-empty set, the one that we have already mentioned, maybe G, has more than one binary operation. If the non-empty set satisfies more than one binary operation. So maybe I'll just write it down over here, because this is the simplest way I can discuss with you on this. So if more than one binary operator applies on G, then we call that as an algebraic structure. Okay? Then it is called algebraic structure. For example, if you take the example of G, as I said, suppose I mention it like this: G, comma, plus, comma, multiplication. So if you observe that in our case, since we have defined G already between minus infinity to plus infinity, we can take any two elements of G and we add up the both and we get the answer. We already have two. Similarly, if you take any element and you take multiplication of it, that also will be a part of the element itself. Even if you take negative values, doesn't matter, because the product will be positive and it will come to like two negative numbers, suppose it will become a positive, or even one negative, one positive, doesn't matter, because it still belongs to G. So the point is, in this particular arrangement, G, comma, plus and multiplication, so there are two binary operations that applies on G. So we will call them as an algebraic structure. Understand? So for any given set, if you consider that there are multiple such operations on top of a particular set, we call that an algebraic structure. So closure property and algebraic structure, these two have been defined by now. Any doubt with this too? Because this becomes the fundamental to the next set of discussion. So for example, if you take I think this is already been proved. Can you check it? You can do it later also. Suppose I give you an example, like I just give you a task, you can do it later also. Suppose you take all the rational numbers and you prove that amongst plus, multiplication, minus and division. Okay? Is it where R is all the real numbers? Sorry, R is real number, set of real numbers. Check for this that whether it is an algebraic structure or not. Suppose you just go and test it later on, not now. You don't need to worry much about the process itself. But the process is that binary operation is now pretty much okay. And we know now the binary operation, more than one binary operation will become a algebraic structure. Now come to the second property. Let's go back to the second property in the PPT. Please make a note of the second property. The second property is where we are discussing if A, B, C are in G. So there are three elements A, B and C. If they are in G, then A operator B, I am talking in general term, A operator B operator C, that is a binary operator, is equivalent to A dot B dot C, where again the dot has the same meaning of binary operator. So associative property is A dot B dot C, A dot B in bracket, as you can see over there. So let's try to figure out with another example. So let's take an example where we take the G example itself, because that's the most easiest one to take for explanation purpose and all. So this is plus 1 and it goes till plus infinity. Suppose this is all the integers we are talking about. And the question is prove that Z comma plus. Okay, so that this plus operator, now we know that this is a binary operator. We have already proved that. Now we have to prove that it follows the associative rule as well. So how we are going to prove it? For example, we take any two elements from the set. So we take maybe minus 5 and 2. Okay, so minus 5 and 2. Now the rule is, as per the formula, A dot B dot C is equal to A dot B dot C. Now this dot will be replaced by plus in our case. So what we are going to represent? A plus B plus C. Let's see in the LHS if I take the elements which on top of it. So minus 5 plus 2 plus maybe we'll take another element as 4. Okay, so A, B, C we require. So 4A is this one, suppose, B is this and C is this. Can you just solve it quickly? What will be the answer? So this is minus 3 plus 4, which is 1. Now you take the RHS again, same way. So it will be represented as, in our case, A plus B plus C. So A is given by minus 5 plus 2 plus 4. So minus 5 plus 6, which is equal to 1. So we are observing that for the set Z, the plus operator is a binary operator. It also will follow an algebraic structure also, and it follows the associative rules as well. Am I clear with this? How we are trying to prove for any given question? This is how we are going to approach. Okay, we will see that numerical with numerical. So associative property is very simple. A dot B, where dot indicates the binary operator. Can you check it for? Let's see. Z comma multiplication. If multiplication is a sign, is it following associative rule? Can you check it? It should follow. It should follow. So that's why you can see already we have proved that plus and multiplication is an algebraic structure. So it should follow an associative rule. So that's the catch over here. Correct? So that's how we are going to do it. So associative rule is done. Now comes the third one. Please make a note again. Commutative rule, because this is where things get a little different. Now the commutative rule is that for all A and B, in G, A dot B is equal to B dot A. Very simple rule. A dot B equal to B dot A. you can very clearly observe that if dot indicates a multiplication, if we consider that dot like z comma multiplication is an operator, so anything that you do 5 into 2 is equivalent to 2 into 5. You are getting the same answer. So without even doing anything, you can prove it very simply. Okay, so but if I consider z comma plus, will it be working? Let's see. I think it should work. Suppose I consider this one and I take two elements 5 plus 2. So this is 7 and you can see 2 plus 5 in the right hand side, that also is 7. Very simply we can prove it. So commutative, associative, closure, three properties we have proved, and it applies for any some number of sets, anything, any set that you consider for any rational number, real number, or irrational number. Also, I think irrational number is more, the operators will change actually. But anyway, so given a particular set, commutative, associative, closure has been proved. Now comes the difficult one. The third one, if you observe, the fourth one. Existence of identity. Please make a note of that. This is where little concept will come in. So the point is here, for all A in G, like for all the elements present in a particular set, there is an identity element E such that E into A is equal to A into E is equal to A. Very similar to A inverse equal to I, the way we do it in matrix. AI is equal to A, right? The identity matrix, if it gets multiplied with a matrix, it becomes the same concept over here. So please make a note of this nomenclature. So for any element of A belonging to G, there exists an inverse operation, inverse element, which will make EA equal to AE equals to A. So let's take an example for it. This is a very interesting example that we come across. So let me write it down for the time being. So we have the identity element. So the formula that we have is A dot E equal to E dot A, that is equal to A. Okay, so that's the idea. Now suppose we have Z again once again and we have plus. We are taking one reference only. Suppose this is the operation. Okay? Can you prove it for yourself how this can be done? So what we are looking at, suppose we take value 4. Suppose my A is equal to 4. I take our element 4. So the operator that we are talking about is plus. So 4 plus something over here such that it becomes 4 over here. What should be the something? 0. So basically we can write something like this. So 0 over here, it will be called as the identity element given plus as the binary operator. Understood? If plus is the operator that we are talking about, if plus is the binary operator applied on a set Z, then 0 becomes the identity element. Can you find me for multiplication? Suppose I give you the answer, I give you the set Z comma multiplication. So you take any element, for example A equals to 4 once again. What will be the identity element for making it this equivalent? 4 multiplied by, operator is now this, dash is equal to 4. So what should be this dash? It should be always be 1. So the point is, for different sets of operator, the identity elements will change, but for the given set, there will exist only one identity element. Please make a note of this. So there exists only one identity element per operation. Okay, so based on the operation that we are talking about, your identity elements will change. Right? But why this is important? Because identity element, based on this identity element, we will prove the next one, which we call as the inverse element. You take the last element. Existence of inverse, the fifth property. Please make a note of it. For each A in G, same way, there is an element A called inverse of A, such that A inverse is equal to A inverse A, and that is equal to E. So E is the identity element once again. So whatever be the identity element, based on the identity element, your inverse element will change. If you are considering a 0, you will have a different set of inverse element. If you have 1, you will have different set of inverse element. So let's prove that also. So inverse element is what we are talking about. So the formula for inverse element is A dot B is equal to B dot A equals to E, or we can also write A dot A inverse or A star, whatever you call it, A star dot A. A star and A inverse, they are different, similar nomenclature, so we can write any one. I will just use it all together so that we are in a position, so that will be equal to E. Can you find me the inverse element for Z comma plus? Can you do it? Take any element, for example, I give you the element 10. A equals to 10. What will be the inverse element of it? Very simple. You can see 10. What is the formula? Dot here is plus. For our case, dot is equal to plus. So 10 plus something, such that for plus, what is the identity element? The identity element for plus was 0. So your right hand side equation is equal to 0. So what will be that gap? Fill in the gap such that it becomes 0. So basically you have minus 10. So you can observe that suppose I take A as 20. What will be the inverse element? Minus 20. So it means that for a given set there will be one identity element, but there can be n possible inverse element based on whatever the elements you are considering, or whatever the numbers you come. Because for every element, if I consider plus as the operator, identity element will always be 0 if the operator is plus. But based on that, we are observing the inverse element will go on as per the dimension of the set itself. This is about the fifth property that we come across. So in general, if we try to take a note of the finding what we have observed, let me just write it down for you, and please make a note of this also so that the clarification is more. So first of all, we have discussed closure property. So closure property correct. So closure property, if we have, we will call that as an algebraic structure. Please see this carefully. Closure and algebraic property is the first thing that we have discussed. Now, if any set or any given operation, if the algebraic structure is following associative property, we usually call that as a semi-group. Please make a note of this. The 5 property that you are looking at, they are called as group, the property of group. If all those 5 are maintained, we will call them as a group element. Now within that, if suppose associative and the algebraic structure is maintained, we will call that as a semi-group. Now if another group or any sub-module of it has an identity element, and the above two, then we will call this as usually monoid, M-O-N-O-I-D. We will not discuss that much detail, but just for your information. So closure property, algebraic structure, associative and identity element, if you have, we will call that whole set as monoid. Okay. Now if you have an identity element and you can find out an inverse element of it as well, then we call this as a group. Just like we have discussed the 4-5 property that we come across. In fact, along with that, we have to add the commutative group as well. commutative property. So specifically, if all this is made, we will call this as an abelian group. Abelian group. So a group that has 5 properties, all the 5 properties, we will call that as an abelian group. It is a group, but it has a separate name of it. So commutative, inverse, identity, associative. So given a question, you have to prove all these 5 properties one after the other in order to get the final answer. Right? Any doubt with the process? It's a process in which we are classifying the element and the operation on top of it. As I said, these are all this operation, the binary operation. If you remember, most of the discussion of the previous existing algorithms we have come across, we actually had done plus, minus, in some cases multiplication as well. Now the fundamental background of it is what we are discussing. In that we are classifying something as group based on something called as algebraic structure, which again depends on the closure property, which again depends on the binary operation. Based on that we are trying to prove it with z element, z as all the negative to positive, all the integer value, and it can be applied to any other set given, any other set of numbers given. So based on that, can you prove for z comma multiplication? Let's see whether you have understood this. Suppose you have given a segment of this z comma multiplication. Can you find the inverse element for this particular set? Can you please try doing it? Let me instead of z value give g. I'll just give it g because that's what we have defined. Suppose we have g comma multiplication. What was the identity element for multiplication? 1. Can you prove that what should be the inverse element of it? For example, you take any value a equals to 5. So the rule is 5 multiplied by something such that it becomes 1. 1 is your identity element, that's why you mention it as 1 in the right hand side. Dash is the element that you want to have as the inverse element, and 5 is the element that you have considered. What should be the value of the dash to make it happen? So it should be either only 1 by 5 and then only it becomes satisfaction. But 1 by 5 is a fraction element. Does it belong to G? Does it belong to GS? Does it belong? No. It doesn't belong. So we can say that for G comma multiplication, there exists no inverse element. If there is no inverse element, if you go back, if you don't have this inverse element, we can say that particular set will be called as a monoid. It can't be a group. Understood? So each and every time you are given a scenario, you have to, if you are making that as a group, it should satisfy all the conditions. That's the trick of it. So keeping that in mind, let's take a example, real example, and try to prove it and see how the numerical should look like. Yes, please. Because we already had done, I think for this one we already did. No, I thought we don't know. It was proving that those things we have proved. But while we are calculating the inverse element, we are finding out that there is no existence. As per the condition is not satisfied. So we can't call that. Please make a note of this question. I'll write it in short because of lack of time. But let's see whether you are able to understand. Let's just write in short, okay? Let A be a set of all positive real numbers. A is a set of all real numbers, and see this carefully. O dash, I am mentioning this way. O dash, this is just a symbol I am talking about. This is an operator. It is a binary operator, I would say, operation, which makes a relationship as A dot O dot B is equal to AB by N. So the question is, let A be a set of all positive real numbers and O dash be an operation on A defined by small a O B. This O is like this, O dash underline B is equal to ABN. For all AB that belongs to A, and n is a fixed positive rational number, let it be. Prove the property, find the inverse and identity element of the same. Prove the property, find the inverse element and identity element for the same. Now how you are going to approach? The point is, whatever happens, you have to find the phi property, you have to prove the phi property one after another. But as you can see, it's very simple. The question is very simple, but the visualization of the question is where it becomes a little difficult. So observe, the first thing is we will try to prove the commutative, for example. So let's take that. So the element was the ideal, the equation was A dot B equals to B dot A. Now see how we are approaching it, and you will follow for all the others. What is dot over here in this question? People at the back, what is dot over here in this question? O underline. That's the operator we are talking about. This is what we have already defined. In the PPT also we have defined this. But what is this dot over here in this question? This is my operator. So basically what it indicates that proof is something like this. This visualization is what makes discrete mathematics little difficult. Nothing else, what I feel. So O underline is nothing but an operator, binary operator, for which we have to prove this. Now, let's see how we are doing it. Now, given the fact that A dot B is AB by N, you can see very clearly. So, in the left hand side, we can easily write it as ABN. On the other hand, in BO, we can easily write it as BA dot N. Now, you can see the LHS and the RHS are absolutely the same. AB by N and BA by N meaning the same, because A and B are all the real numbers. So, the overall meaning is the same. So, we can clearly say that both of them are same. So, the LHS is equal to RHS. So, for the set A, the commutative property is maintained with respect to O underline operator. That's the only thing that is. Can you quickly give me the associative in the same manner? Can you prove me the associative also? Associative was A dot B dot C was equal to A dot B dot C. So in our case it should be A O B C A O B C. Take the left hand side, take the LHS. AOB is gone by AB by N C. Are you following it? What I did? A dot B, this one, it's already given, it satisfies this equation. Now, this AB part and this one again forms, we can relate it with the given condition. So, we can write it as ABC by N. And same way you can prove it from this side as well, that this is also ABC by N. Sorry, N square. Sorry, N square. Sorry. Because C here will be, for people if you are not able to understand this. So this is AB by N. So this is my A actually. And this is my B actually. So this is how it is represented in between. Now we are given AB by N. So basically in between step is C by N like this. So that's why this N square comes in over here. Understood? So LHS is equal to RHS. So in that way you can find out the inverse element with the same condition given. Can you quickly do that? Inverse element or for that matter identity. First find identity. Without that you can't do it. Just take 2 minutes to find out the identity element. What was the condition for identity element? A dot E is equal to E dot A equal to A. Right? So in our case, suppose A dot E. So what did it look like? Something like this. Now you apply the same rule again on top of it and find me the answer. So it should be, so the E is equal to N, it's coming in. Do I need to solve this? Are you able to do it? This is what will be coming, right? LHS if I do it. So your E is something like NE by NA by A. So it gets cancelled. So your E is basically N. So for the given set, N becomes the inverse identity element of the same. Same way you can prove it, the identity element as well. So as the commutative, associative, inverse, closure, as well as the inverse element are present, we can say that this is an abelian group that we are looking at. Similarly, you can take any other example and you can prove it. Right? Okay. So we stop the session, we come back next day and we continue for reading and others.